Sir, shall we start, sir?
Yes, we can.
Okay, sir. Thank you, sir. A very good morning to all the participants from various institutions, industries, and the faculty members of Anna University. On behalf of Institute for Energy Studies, Anna University, I take an immense pleasure in welcoming our distinguished speaker, Dr. R. Sethumadhavan, sir, Professor Emeritus, Anna University, Chennai. He is a great administrator, wise academician, and industrial consultant, and an eminent researcher, and now is currently working as a senior director, GSH Energy Service Private Limited, Chennai. Sir having vast knowledge in the field of energy auditing, energy conservation, waste to energy management, and renewable energy. Sir is a accredited and certified energy auditor for DISCOM and the petrochemical sector. Sir has more than 34 plus years of experience in teaching and in energy auditing. Sir has conducted more than 100 plus energy audit in various sectors include agriculture sectors, automotive, cement industries, commercial buildings, power plants and textile and more. Sir has completed total 16 consultancy projects and he has published numerous research papers in various international and national journals. We are very pleased to have you here, sir. With this introduction, I request you to deliver a technical talk on boiler losses and its mitigation, sir. Over to you, sir.
Thank you very much, Mr. Shyam. Let me thank Institute for Energy Studies, Anna University, Director and his colleagues for giving me this opportunity to talk about energy losses in boilers and the methods to mitigate that. This is one of the most relevant topics, especially after the presentation of the 2022 budget by our Honorable Finance Minister, where she has said that power plants will have to be more efficient and also will have to cut down their CO2 emission. Carbon dioxide emission has to come down. And for that, she has suggested, given an antidote that is going in for partial replacement of coal by agro residues. 6 to 10% is what the number suggested by her. And this is one of the, I would say, the great steps in the right direction. As we know that power plants are the lifeline of the industrial activities, and at the same time they also pollute the atmosphere by way of CO2 emission. So in that circumstances, the present topic, not only the topic of this session, the topic for the entire 5 days program, that is power plant related, rather energy related activities of power plants, are going to be discussed in detail. And I could see that there are talks about which will be delivered in the coming sessions today, tomorrow, later, on steam energy conservation, electrical energy conservation, energy conservation on the rotating machineries, etc., etc. So to start with that, I think it is right thing that the energy conservation on the boiler, what you call as a thermal energy conservation. That is a topic we start with, and later on I think we will be having the energy conservation aspects of auxiliaries also, in addition steam. So let me thank the organizers for this opportunity, and let me start my lecture now. Now it's 11:40. What I'll do is I'll try to finish by 15 or 20 minutes past 1, and we'll have about 15 to 20 minutes for interaction as well as question and answers. So let me start with my lecture now. Can I go to the first slide, Mr. Shyam?
Yes, sir. Sir, I changed the slide, sir.
Yeah, start we can. I could not see the slides.
I think it is in presentation mode only, sir.
I am unable to see it.
So you can pin my name, sir.
Yeah, I think I could do that. Okay, now I could see that.
Okay, sir, sure, sir.
So this is the performance related aspects of thermal power plant boilers. So as I said that the entire session of 90 to 100 minutes we are going to talk about the boiler related aspects of the thermal power plant. Although the boiler related aspects I said in thermal power plant, it's basically the boiler study. We are going to have a look at that. So a bit of a thermal engineering understanding is a kind of a prerequisite. Of course, it's not going to be a difficult one to understand. I'll be making it as simple as possible. And if you see it on the screen and the title, I have been awarded the AEA 315, that is my number. AEA stands for Accredited Energy Auditor. This is again given to the people who are having expertise in certain areas. Like for me, it is on the DISCOM, that is power distribution companies, they call it as DISCOM, and also the petrochemical. The reason for that is that I have carried out a couple of energy audits, mandatory energy audit in this sector. So now I have been authorized as an accredited energy auditor for carrying out energy audit in this sector specifically for Government of India, and especially in the PAT scheme, perform, achieve and trade scheme, where a lot of things are happening by way of implementing energy conservation scheme. So that is what this AEA stands for. Now let me go to the second slide. So it's important that we need to understand the necessity for the discussion on this power plant energy conservation with specific reference to boiler. You can have a look at that. About 210 out of 420, 50%, and to be exact, it is 53.3% of the energy, 420 GW gigawatt. Coal-based thermal power plants occupy 53.3%. It used to be two-thirds earlier, about 10 years back. It used to be two-thirds, that is 63% of our energy, so the 66% of our energy was coming from coal. Now, due to the aggressive effort put in by our government, the renewable energy, solar, wind, they are all picking up. So the percentage contribution of the renewable energy has gone up. In other words, it has brought down the percentage contribution of coal-based TPP. But said and done, coal is the major lifeline of our energy scenario in India. We cannot live without that. Only thing is, over a period of time, we should be able to bring down its contribution in the overall power scenario. Like it has come down to 53.3. Maybe in a couple of years, it might come down to 45. Maybe we aim something like 1/4, 25 or 30%. But one thing has to be very clear, that it cannot become zero in the near future. And like our PM has said, 2050 could be a possible time when we may say that CO2 emission has come down, not necessarily the coal usage has come down. We'll be seeing that how come coal usage will not come down but CO2 will become zero. That we'll be seeing it as we proceed. Right now, this is the scenario. 1600 trillion watt hours is the energy generation from coal-based power plant, and it consumes about 1500 million tons of coal, and the emission is 2300 million tons. So you all know that CO2 is going to come out whenever you go for a thermal route. It is as simple as that. Even if you burn, let's say, agro residues, you are going to generate CO2. You are going to see that basic stoichiometry equations say that C plus O2 giving CO2, and that is an exothermic reaction. So energy is going to be generated. So energy generation is certainly accompanied by CO2. So wherever we have energy generation through thermal route, that is combustion route, CO2 is going to get evolved. No escape from that. But the CO2 that is coming out, if it is from biomass or agro residues, we call it carbon neutral, because whatever CO2 that is getting emitted is going to get reabsorbed by the growing of plants. So that way, usage of biomass will bring down the net emission of CO2. We need to be very clear that even biomass combustion will generate CO2, but that CO2 we call it as a recyclable one, which will be absorbed by the plant. So net CO2 emission would come down. So that is the strategy which is being planned. And of course, the second one is absolute reduction or zero of CO2 emission. So we need to adopt non-combustion route like solar and wind. Municipal solid waste, yes, they do generate CO2, but again, it's a waste to energy. So that way, the idea is look for various options for CO2 emission reduction. And for that, you can see that coal consumption must be reduced. One possible way out is energy efficiency. Energy efficiency in boiler operation. The second one is alternate fuel like renewable fuel, hydro, nuclear, etc. The work is going on in that field already. Similarly, energy efficiency is also being attempted to a very high extent in thermal power plant. We should really feel proud of that. Majority of the power plant, they really operate efficiently. But still, because of the CO2 emission, we are trying to look into the possible areas for CO2 reduction. That's the reason why we are talking about thermal power plant boilers. We go on to the next one. Way forward to achieve energy efficiency. One, establish the actual performance of the boiler in terms of thermal efficiency. Quantify various heat losses associated with boiler operation. And of course, make efforts to minimize the losses and sustain it. Total elimination is not possible, that also let's understand. So the idea is, let's try to establish the thermal efficiency of the power plant boilers, and once you do that, you will be able to understand the types of losses that take place, and also we can quantify the same. Once you are quantified, then I think we can make our sincere efforts to reduce the losses. As I said, the losses are inherent part of the system, so they cannot be zero. They cannot be made to zero. We shall try our best to minimize it. So once that happens, naturally the coal consumption would come down, and once it comes down, you all know that emission is also going to come down. Now these are the boilers are classified: high pressure, medium pressure, and low pressure. We will be talking about high pressure boiler, thermal power plants. Whereas when you are talking about the cogeneration sugar mills, they come under either MP or HP. I say MP or HP because the older versions of cogeneration boilers, they operate around 65 bar, that is 20 to 80 bar range, medium pressure. Of late, even the cogeneration boilers, they are getting designed for high pressure steam, so they come in 80 bar and above. And the LP, that is 20 bar and less, they are all called low pressure, and they are basically classified as a process boiler, process industries, where you need a saturated steam, for process application. In a saturated steam, you all know that latent heat is higher and they are not getting superheated. So the maximum thermal energy conversion happens at the LP boilers. So our focus is now going to be on HP-MP boilers, that is power plant boilers. This is a typical boiler circuit. This can be applied to even to the process boilers. You have boiler, fuel coming from the storage yard, and then we have the water circuit. Like you can see the condensate tank on the left hand side. Then you have deaerator, you have an economizer, and on the right top, steam to the facility. And flue gas path, you can see FD fan. Then the flue gases go via economizer Then you have pollution control equipments, and then to the stack. So there will be 3 or 4 distinct circuits in the boiler operation, be it process or power plant, and each one circuit has to be separately dealt with to understand their efficiency of operation. Once that is understood, I think we are done with that in terms of understanding the possible efficiency enhancement in the thermal operation of the boiler. Yeah, this is the other way of looking at that. You can see that the dotted ones, there is a air circuit, there is a fuel circuit, there is a feed water system, and there is a stack circuit. Because each one has a role to play. We all know that basic stoichiometry talks about supply of oxygen for the fuel. Fuel we call it because it has energy content in that, what we call as a calorific value. The calorific value comes from carbon and hydrogen present in the fuel, and that's why we call it as hydrocarbons. When the hydrogen percentage is substantial, then the compared to carbon substantial, then the fuels are very specifically designated as hydrocarbons. That's why we see all the petroleum fuels, we term them as hydrocarbons because they go by the refining process and come out with gases like starting with C1H4, what you call as a methane, C2H6, C3H8, C4H10, C5H12. These are all hydrocarbons like methane, ethane, propane, butane, pentane, hexane, so on and so forth. So that is the fuel. And of course, you have seen earlier, there are power plants that use gaseous fuel also for power generation. And like all of us know that gaseous fuels are the best fuels in terms of combustion efficiency. At the same time, we also know that the cost is prohibitively higher in our country. That's why we don't normally see the gas-based power plants, and of course oil-based also, because both these commodities are quite expensive and very limited availability in India, and they have other uses also. So that's why we don't go for that. So we settle down for solid fuel. And solid fuel, when we say, immediately what comes to our mind is coal. And here you can see that air circuit, fuel circuit, flue gas, water. To split it simple, we know that water is going into the boiler. Now my request is you just imagine just a boiler, don't really need to understand with reference to, let's say, power plant or the process. Let's just talk about the boiler. The input to the boiler is one, fuel, two, air, third one is water, and they come out respectively as ash. Coal gets burnt or the fuel gets burnt and come out as ash, air getting converted into flue gas, and water in gets converted into steam. So 3 in and 3 out. So it's quite obvious that if we need to achieve a very high level of efficiency, the three streams that are getting into the boiler, coal, rather fuel, air and water, they should come out at, or they should come in at highest energy levels possible, and what is going out should also have energy content. For example, the steam should have very high energy content, whereas ash and flue gas should go out with least energy content, so that the all energy that are getting converted from the fuel to the useful one gets absorbed by steam, and that is what we want. So in terms of simple terminology, what you need to do is increase the energy content of input streams, bring down the energy content of output to specific streams, which are flue gas, you can see as a stack, and the ash from the boiler. If this happens, I think we have achieved our goal of energy efficiency. So when we do audit, we try to focus on these aspects. And you also may be knowing about the power plant, where the auxiliary power consumption is also playing a role. Auxiliary power consumption, like you see it on the slide, there's an FD fan, and you'll be having an ID fan, you'll be having a feed water pump, etc., etc. All these auxiliaries, they are all called auxiliaries, they do consume power, and that power again comes from the overall system itself. And of course, when you reduce that auxiliary power, to that extent your power export becomes more. This is what people would really like to look in. But again, as I said at the beginning, my lecture is going to be on the thermal aspects. That is how the boiler behaves in a power plant, not really on how to make the auxiliaries operate more efficiently and consume lesser power. Those topics would be coming in subsequent sections, maybe in a day or two. So this is how the overall system would look like. And again, you can see that superheater is another thing added to the power plant, and there is a turbine. There's a turbine, and superheater is the another system which you will be finding very specifically in the power plant boiler, not really on the process boilers. And this is the extended version, and here if you see it, I have mentioned this as the flue gas circuit. Flue gas circuit, as I said earlier, the energy loss in combustion is mainly due to the energy that is going out in the flue gas. And of course, like what I said, it cannot be made to zero. We need to ensure that the energy that is going out of the circuit is the minimum. For example, you can see there is the stack, and the stack we should get the flue gas, not only in terms of quantity but also in terms of quality. That is the quality, when I say the unburns as well as the temperature, they should be absolute minimum. Unburn should be as low as possible, and of course the temperature also should be as minimum as possible, that will not affect the chimney. So if that is taken care of, I think our performance of the boiler would be certainly go higher. And if you see it on the flue gas part, there is an economizer, there is an air preheater. Then we have the ESP, you can see a box like thing, that is, we call it as electrostatic precipitator. These are all very specific to the power plants. And then we have an ID fan, chimney. Why specific to power plant? The power plants boilers, they go for the atmospheric fluid bed combustion, or they go for pulverized fuel combustion mostly, majorly. The reason is that the combustion will be excellent when you go for fluid bed combustion or when you use a pulverized fuel. Pulverized fuel, if you see, they are almost like the liquid burning, or what do you call as a gaseous fuel burning. They burn what do you call as the volume burning, and suspension they burn. So it's a volume burning pulverized fuel, and they operate or they burn to a very high extent because the particulates are so small in size, their surface area will be much more for a given volume. The other one is a fluid bed boiler. This fluid bed boiler, they use up to 6 millimeter size fuel. And here if you see it, the finer the size, better would be the combustion, and you can go for pulverized. But we need to understand that pulverizing a fuel is an energy intensive operation that requires energy, that too electrical energy. And you all know that electrical energy is the costlier form of energy. So when we talk about energy efficiency in combustion, we should not look only as combustion in situ. It is overall, we will be spending money for pulverizing the fuel, so that also should be taken into account. So normally pulverized fuel combustion is adopted when the quality of fuel is low or poor. If the fuel quality is better, we'll be seeing it as we proceed. Then we go for fluid bed combustion, because fluid bed combustion can take fuel up to 6 millimeter size, and the efficiency of combustion can be certainly above 95%. And of late, even the process boilers, any industry you take, they all go for AFBC, we call it atmospheric fluid bed combustion, because of the high efficiency it offers. So in the boiler, if you are really looking for energy conservation, flue gas circuit has to be very clearly understood. In addition, the combustion phenomena that is taking place. So it starts with combustion, and then the energy is getting released to flue gas, and the flue gas shares it with steam, incoming air, high pressure feed water, before it goes to the air pollution equipment, what you call as the electrostatic precipitator, where the unburns get collected, and then it goes to the chimney. So this is how the overall circuit would look like. Now the selection criteria for the boiler. One is the working pressure and the steam quality. Then the steam generation rate, load factor, reliability and efficiency of operation, initial cost, operation and maintenance cost, and of course the miscellaneous like floor area availability, etc., etc. So these are all the parameters to be understood, and from that the selection has to happen. Now the fundamentals required to understand the boiler performance are: 1. Combustion chemistry of fuel. Second is the fuel composition. Third, of course, the steam properties and the terminologies that are normally used. The combustion chemistry is going to give you about the flue gas also. So if these three things are understood, then we may be able to proceed further in understanding the the performance level of boilers, or the way to evaluate the performance. And again, I emphasize on trying to do a lot on the fuel and the combustion, because these two, if are taken care of properly, it is quite likely that your efficiency of operation would be much higher. The fuel is a important part of a thermal power plant, like what I said. Not only thermal power plant, even for process industries. The process industries, they too generate steam, and the steam goes for various process operations. And the steam generation involves the fuel, and the cost of steam is based on the cost of fuel. And there's a terminology called steam fuel ratio, that is in process industries. Whereas in power plants, the terminology is heat rate, heat, H-E-A-T, heat rate. When we talk about steam fuel ratio, it's a question of how many kgs of steam you get per kg of fuel burnt. Per kg of fuel burnt. And of course, it is very obvious that the ratio should be higher. Higher the ratio, lesser would be the steam cost. Because we all know that whenever we talk about energy conservation, energy efficiency, our aim is to look for cost conservation. When the steam cost is evaluated, it has the components like fuel and the manpower involved and miscellaneous cost by way of maintenance of spares and housekeeping, so on and so forth. And if you evaluate, you will see that almost 85 to 90% of the steam cost will be because of the fuel, that too in a process industries, and this should be about 85% in case of power plants. So the major cost of steam is because of the fuel, and major, as I said, it could be 85% and above. So if at all we want to conserve, or what you call the reduced steam cost, it's very obvious the fuel cost is cut down. Other costs like manpower, maintenance, etc., they do follow a standard norms, and they cannot be cut down to a below a certain level. So the idea is how to cut down the fuel cost. Two methods. One, of course, go for the energy efficiency. Second one is go for reduction in the fuel cost. In the sense, we can go for inferior fuel, inferior quality, where the cost will be lesser per ton. But we need to understand that when we go for inferior quality fuel, our steam fuel ratio also would come down. Again, it may not really of much use. We come back to square one. So again, the emphasis is more towards using a good quality fuel and of course to an efficient level. Now this is the coal. Since we are talking about power plant, coal is the fuel, and you can see how the coal is being used here. So this is called the ground level bunker. So you can see the JCB at the background, and beyond JCB you can see the storage yard. Normally about 7 to 10 days of inventory is kept in a power plant. 7 to 10 days of inventory. You would have read in newspaper recently also. There's something like, what do you call, there's a shortage of coal and then it's only 2 or 3 days availability is there, etc., etc. There's a panic, and of course the coal supply was rushed, and then
నేను ఏ రోజు ఆయన
sorry,
వచ్చింది ఇవాళ ఆయన 4 days రావట్లేదు ఆయన 4 days నుంచి రావట్లేదు సార్
so
ఆయన బీరువాలో ఉన్నాయి సో నీకు
it was ensured that the coal was made available. So this is the coal as a fuel, and this is how the transportation would take place. Normally a belt conveyor. Again, you must be wondering what is the need to show this. As I said, in coal combustion in a power plant, tons and tons of coal will be stored in the yard, and there will be losses in the handling, and these losses also would go into the account of the overall usage. So the boiler may be efficient, but still your coal consumption could go higher because of improper, poor handling. So there will be a checkpoint in the power plant everywhere to ensure that coal is not being wasted, or what you call the spillages, or to be very precise, they call it as a carpet loss. The losses are minimum, that is the coal that is not going into the boiler has to be kept at the minimum. Normally 2 to 3% they allow. So that is the extent to which we need to ensure that whatever coal we receive, 95% and more should go into the boiler, and only 3% or 4% is permitted as the losses due to handling, transportation, etc. So the coal transportation also becomes a very important aspect of power plant. And if some of you have visited the power plants or even the process industries, if you see that the boiler, the importance given to boiler operation is more, or I would say that it is equal to that of the importance given to the coal handling also. They call it as a CHP. Okay, in industrial terminology, CHP stands for coal handling plant, and conventionally we say it's a combined heat and power. So that CHP, you just keep it aside for a while. When we say CHP in thermal power plant parlance, it is called combined heat, coal handling plant. Coal handling plant that is also being really targeted for energy efficiency by the commercial department. They also have a role to play in ensuring that they get the right quality coal so that these losses are minimum. In the sense, when we are talking about energy efficiency, I would like to emphasize that do not consider only the boiler as a piece of equipment where energy efficiency can happen. We need to start from the unloading of the coal from the, we say, the truck, and right up to the feeding into the boiler. We need to ensure that the losses are kept to the minimum. So all the coal handling equipments, including the hammer mill, dust collection equipment, fans, belt conveyor, and JCB, everything has to be in pick and span condition so that the losses are kept to the minimum. Otherwise, these losses also would go into the account of boiler, and as an energy engineer, you would be wondering, look, why the efficiency is so low despite the operation is being very efficient, and that would be because of uncaring of the fuel in the handling plant. So the, you can see this is a bed conveyor, how neat, and you can see on the sides also it's almost would be kept absolutely neat on a daily or shift basis to ensure that nothing is lost. And again, another aspect to be understood is you can see the belts are made out of rubber. The spillages, they could be a fire hazard. They are all in a closed system, so there could be heat generation, and once the heat generation happens and then if it catches fire, the belt would get damaged, and once the belt is damaged, fuel transportation cannot happen, and that can hamper the boiler performance. In the sense, as a practical engineer, we need to give consideration to the all the aspects, not only the combustion part of the fuel. And this is a typical example. You can see that absolutely clean environment is maintained around the coal belt, or what you call the coal handling plant, to ensure that wastage is minimum and fire hazard also mitigated. And this is the bunker, and they'll be having many number of bunkers depending on the size of the boiler, and these are all mechanically operated, like what is it, O&M, operation maintenance of all these rotating machineries, is again an important aspect. The reason is the whole machineries, they all operating in a dirty atmosphere, like fuel, powdery fuel, and one, of course, that could be a fire hazard. Second thing, that also will make the equipment operation bit sluggish, and it can get into the, what should I say, that kind of what do you call that, motor, and then coil burning, heat generation, lesser heat dissipation. There can be many things, and each and every part of the power plant is very important. So it is equally important the housekeeping is done very effectively so that the performance is maintained. So coal feeding, you can see that right from the JCB right up to the coal feeding, everything has to be in a clean atmosphere and it has to be cleaned. So if you happen to visit a power plant, please do make a visit to the coal handling plant, not only the boiler, and you can also have a look on the surroundings of the boiler and you can see how clean they are. So this in fact indirectly helps the performance also. Now coming to the coal, and I think since you are all teachers, you must be knowing what you call as a proximate analysis, and other one is the ultimate analysis. The proximate analysis talks about the fixed carbon, volatile matter, ash, and also the moisture content of the fuel. And ultimate, as the name suggests, it breaks them into the individual components like carbon, nitrogen, oxygen, sulfur, ash and moisture. This is ultimate analysis. This is for a typical coal sample. And what do you mean by typical coal sample? It could be coal from any source. We will be seeing it a bit later. And there are many terminologies that are used to define the quality of coal. As received, air dried, as determined, ash and mineral matter free, so on and so forth. And the moisture also, you have surface, inherent and residual moisture, ash and volatile mineral matters. They form the overall mineral matter. In the volatile, again you have the organic. So there are many ways of defining a coal. Many ways of defining a coal. The emphasis is more towards understanding the coal properties, because in power plants tons and tons of coal are being consumed, and the coal is also being procured in large vessel in the sense I mean the ships, and the smallest ship would be able to carry about 100,000 1 lakh tons of coal. That is the size of the smallest ship, and the coal comes and gets dumped in the shipyard. From there it will be moved through either railways or through trucks to the user point. So the coal undergoes drying at various locations, right from the mining and then to the loading point, and then during shipment, unloading point, from unloading to the user point. So it gets transported all the way. So as it gets transported, the moisture level gets reduced normally, and then of course the volatile also start escaping. So the quality of the coal that is mined would be different from the quality of coal that is getting burnt. So, and you all know that it's a very costly commodity, and a good quality coal has to be not only procured but also fired. If the coal is not carried during transportation, again we can get into a problem of higher fuel consumption and of course loss in the transit. So the coal is well defined by the supplier as well as the user, and based on which they go for the purchase. And you see that there are 17 grades of coal. 17 grades of coal. This of course very specific for power plant. G1 to G17. G17 is as low as 2200 kilocalories per kg, and G1 grade could be 7000 and above. So question is, what is that we are talking about? Which coal? Is it G1 or G5, G11, G14? And it varies from mine to mine as well as from country to country. And it's also obvious that lower the calorific value, lower will be the cost. When the cost is lower, of course, steam generation, when the quality is low, steam generation also will be low. That is, steam fuel ratio will be less. So you may not get any cost advantage. And many a times it may not be our choice on the coal quality, because we need to buy what is available, because the quantity required is tons and lakhs of tons per year. So we need to live with what is available, considering the quality as well as the quantity, and try to improve the performance with the given fuel quality. And you can see the table. Basically these are the 5 sources of coal as far as India is concerned, rather Indian power plants are concerned: Indonesian, South Africa, Australia, USA, and India. And you see that second and third, total moisture, ash content, very important parameter. Rather, ash is one of the deciding parameters, because when the ash content is high, the energy transported per ton becomes lesser. When the ash content is small, the load on the dust collection equipments goes higher. That too consume energy, and ash disposal also would become a kind of a action nuisance to be taken care of. So industries, they look very seriously the ash content part of it. The second one is moisture content. Moisture content, of course, it could be, it is not as critical as that of ash, because you all know that moisture can be added or removed. And a fluid bed boiler, normally up to 30% moisture it can take and burn the fuel effectively, not a difficult task. So if you see that A or B, as received basis, ADB stands for air dry basis. And in India right now, underline right now, Indonesian coal is being used by all. We don't go for Australia, South Africa coal because they are quite expensive. You can see their GCV, calorific value. And USA, of course, the transportation is a very high cost. So, and if you look at the Indian coal, ash content is very high, energy is also low. So right now in India, Indonesian coal is being the one which is used to a very high extent, and this is where the, you must have read at least 2 months back, the crisis came, because all the Indonesian coal were being purchased by Chinese people, Chinese government. So the coal price, you will be surprised. The Indonesian coal used to be about 5,500 rupees per ton. It had gone as much as 15,000 rupees per ton, 15,000. And of course now the prices have softened to 7,000, but still not to the level of 6,000. And all power plants, they were finding it extremely difficult, and then they started mixing with Indian coal, although they have a lower calorific value and high ash content, but still the cost is the factor. So it was also mixed with the Indonesian coal, and right now the situation is slowly coming back to normalcy. So if you really look at that, Indonesian coal is the most preferred coal as far as Indian power plants as well as the process industries are concerned. And this is the typical composition. We call it as a GAR. GAR. This is the terminology normally used in by coal dealers and coal purchasers. GAR stands for GCV as received. GCV, that is gross calorific value. A stands for as, R stands for received. So there are two grades as shown here. There is one more grade, 5,200 GAR also. And you see that calorific value is the GAR, 4,500 GAR, in the sense it will have a GCV of 4,500 kilocalories per kg, and this is the moisture content, ash, volatile matter, so on and so forth. So this is how the coal is being selected. Like what I said, before going in for efficiency, we need to ensure that the best quality coal or the quality of coal is understood by us before we embark onto the efficiency aspect. Like if you go for Indian coal, certainly the operating efficiency will be lesser because of the higher ash content, and also the auxiliary power consumption will be more because of the power consumption by the downstream equipments, especially the pollution control equipments. So when you use the Indian coal, your parameters will be different and your efficiency also will be different, including your auxiliary power consumption. Whereas when you go for better quality coal, they would be different. So this we need to understand while going in for the performance prediction. And this is the typical representation. You may be thinking that I am spending more time on the coal or the fuel related aspects, because I know that this is the most important parameter in a power plant operation. If the coal is not of the right quality, then you cannot achieve the efficiency. So we also insist on all the power plant before we go for the audit or before we certify the efficiency level, we completely get the parameters of the coal purchased. Again, the coal purchase would go different quarter wise, because normally the coal prices they go by the coal index international market, and they're all fixed for only 1 quarter basis. Every quarter there will be a change in the coal price, and again when the coal price changes, the commercial department of the power plant may look for a cheaper coal because they would like to freeze the cost, so they may go for a cheaper coal. And you all know that when you go for a cheaper coal, the performance get a hit. So when we do the energy audit, we not only look at the process parameters, efficiency of boiler operation, we also get the analysis of the coal and type of coal used, cost of coal used in the previous 12 months minimum. We normally go for 24 months, based on which we try to establish the performance. And if you see it, a J calorific value is 4692 ARB, and when you go for a dry ash free, it is 6869, but of course the 100 kg has become just 68 kgs. So this slide would be of useful to you. You can just see it when you have a leisure time, how the quality or the how the coal is being, what should I say, specified by the supplier, because many power plants they had to be doubly careful before understanding the not only the cost but also the quality. So there are many ways of defining the quality, like ARB, as receipt basis, air dried basis, bone dry basis, dry ash, mineral matter free, all those things. And as you go down in this, yes, you can see the GCB increases, but the weight also comes down. So these are all the various types of representation of the coal properties, and this is one of the most important parameters, moisture. Like what I said, ash is an inherent property of the fuel. So what I mean is that the ash content cannot be added or removed, whereas the moisture, it can be added or it can be removed, or it can also be influenced by the environmental parameters. For example, if you take a coal during rainy season or the coal is mined during rainy season, naturally the moisture level will be higher. And the coal what you get during rainy season, the rain may be on the mining site, not necessarily at the user site. If it's on the mining site, inherent moisture will be higher. If it is raining on the user side, then you will have that surface moisture will be more. And in addition, the moisture also can get added, because mostly the coal is being transported from country to country by sea, While shipping, you know that it has to travel days and days on sea, and then moisture pickup will be there. So it is normally the coal at the deep port at which it is unloaded. The performance is sample is taken and the performance is analyzed, based on which the cost is fixed. So the moisture can play a role in the coal cost as well as the performance. As the moisture content increases, the calorific value comes down. This, of course, all of us know. Then come to the combustion aspect of that. You know, the excess air, stoichiometric air, and substoichiometric air. Of course, as far as the combustion is concerned, it is more of the excess air that would go into the combustion. Stoichiometric air or substoichiometric. Substoichiometric air, you all know that go for gasification process. Gasification, where you don't really supply the required quantity of air, we supply some percentage of the theoretical air. That percentage is less than 100. Stoichiometric air is one that is the right quantity of air, 100% we give. Whereas the actual air, we certainly go for some safety factor incorporated in that. So if you have to supply 100 kg as the theoretical air, we may be supplying more than that. This more depends on the type of fuel, type in the sense not only quality but also like is it a gaseous fuel or a solid fuel or a liquid fuel. And you all know that solid fuel calls for a higher excess air. The excess air could be 40%, 30 to 40% for a solid fuel, and it will be as low as 5 to 8% for the gaseous fuel, and for liquid fuel it could be about 20 to 25%. So the excess air is a must, and of course I don't want to go in depth about what is the excess air and why you need to supply, etc. For a complete combustion to happen, we need to supply some amount of excess air, and only thing is that excess air should be optimum excess air. It should not be excess air in the sense, it's very clear, it is more than what is needed for efficient combustion. So anything that is supplied above the requirement is going to go as a waste. So the excess air here, if you keep it 40%, that's an ideal one for the solid fuel. And if you keep it 100%, 200%, 150%, it is waste of energy. So energy is getting diluted and then thrown away or taken by the flue gas. So the excess air has to be properly evaluated and kept under limit. So the combustion, we always talk about excess air. Stoichiometric air and substoichiometric air, they don't find a place in the complete combustion. And here you can see that a visual observation. Complete combustion, it is almost colorless, and in fact it should be slightly hazy brown. It should not be colorless also. Colorless says that yes, combustion is good, but thing is the excess air is also on the higher side. And you see it on the right hand side, it's an incomplete combustion. You can see that black smoke coming out. The black smoke is nothing but presence of carbon, and presence of carbon obviously indicates that the energy is lost in the flue gas, and that energy goes unburned, and this also results in pollution of the atmosphere. Now the steam related aspects. So we have seen parameters related to the coal, how to select a coal, and we also seen that combustion related, especially the excess air, what should be that. And third one is, since we have talked about the coal as well as air, the third input parameter is the water. that is coming out of the boiler as the steam. Let's see what are the steam related parameters. One is the equivalent evaporation. This you must have seen in your second year or third year heat transfer, or maybe the power plant, or even in boilers. Quantity of dry saturated steam generated per unit time, maybe second, minute or hour, from feed water at 100 degrees centigrade to the saturation pressure corresponding to 100 degrees centigrade. This is equivalent evaporation, and we also call it as the F and A 100 degrees. This is the terminology normally used in the boiler nameplate. If you say 10 TPH, 10 tons of steam per hour is the generation, that is the nameplate indicates. In that one, they also call it as a from and at 100 degrees. In this sense, if the water to the boiler drum is supplied at 100 degrees centigrade temperature, and if the steam is taken at 100 degrees centigrade, that is the saturated steam at atmospheric condition, so you have fixed the enthalpy rise, that is 540 kilocalories. For that, the boiler will give you 10 tons. If it's a 5 TPH boiler from under 100, it means water is supplied at 100 degrees centigrade and steam is taken at 100 degrees centigrade, then the boiler will be able to give you 5 tons of steam. In other words, the energy content will be 5000 kg per hour into 540 kilocalories per kg. Normally, if you really look at the thermic fluid heaters, the energy content is the output parameter for the thermic fluid heaters. They say that this is a 1 million kilocalories per hour TFH, thermic fluid heater, 2 million, 5 million. Similarly, boiler also meant in terms of kilocalories, but the terminology somehow has become tons of steam per hour. So we need to understand this parameter in an equivalent evaporation, because in reality all of us know that the feed water to the boiler cannot be at 100 degrees. Similarly, the steam pressure also will be, even for process industries, it is 10 kg per square centimeter, corresponding to 170 degrees centigrade. So, in reality, boiler water temperature may be 40 degrees centigrade and steam may be coming out at 10 kg per square centimeter saturated condition. So, the enthalpy would be much more than 540 kilocalories. So, the steam generation rate will be lesser. In the sense, we need to understand the capacity of the boiler for the condition in which we are operating. The nameplate suggests information which is under standard condition, whereas that has to be modified to the operating condition. This is what we call as a equivalent evaporation. And this is the factor of evaporation. This again based on the steam enthalpy and water enthalpy, like what I said. If the water is at 40 degrees centigrade and steam is at 170, so it may so happen that the energy required would be 660 kilocalories, not 540. So the steam generation would be 540 by 660. That is maybe 80%. 80% of the nameplate steam generation. So a 5 tons boiler can give you 4 tons. So we need to understand this equivalent evaporation as well as the factor of evaporation. Now comes the key performance indicators. Of course, you may not find this in the typical textbook, but these are all quite relevant to the industrial application. Mass loading, Energy loading.
பண்ணிட்டேன் மேம். பிரவீன்குமார் பண்ணிட்டேன் மேம். இப்பதான் ஸ்கேன் பண்ணிட்டு இருக்கான்.
Direct efficiency as well as the
Submit
indirect
போட்டா மேம்.
efficiency. So these are all the terminologies used to define the key performance indicators of a boiler operation. As I said, you may not find it in textbook. Now, what is mass loading? Mass loading. Somebody has to mute the mic.
Yes, sir. Doing, sir. Participant, please kindly mute yourself because it creates disturbance. Yes, sir. You can proceed, sir.
Shyam, I had the option for muting all. I have done that. Now, sir has to unmute himself.
Yeah. Thank
Okay,
you.
sir.
Now, this mass loading. Mass loading is a parameter like you know what is the quantity of steam produced and you compare that with the boiler rating. Like you produce 4 tons of steam and the boiler rating is 5 tons or let's say 40 tons and 50 tons. You say that mass loading is 80%. That is how the industrial understanding goes. I'll tell you whether it is right or not. Then comes the energy loading. Energy loading is nothing but the what is the energy content of the steam produced that is coming out of the boiler to that of the designed energy content of the boiler. If it's a 10 tons per hour boiler from and at 100 degrees centigrade, so it is going to a 540, that is 5,40,000 kilocalories per hour as the energy output possible from the boiler. That is the design condition. This you compare it with what is steam generator and what is the energy content. So this is we call it as energy loading. And of course I will show you a what do you call the sketch where you will understand the meaning of that. And third one is the direct efficiency, where we try to establish the steam enthalpy as against the fuel consumption multiplied by fuel calorific value. Then indirect efficiency, this is trying to establish the losses. From that we go to find out what is the efficiency by indirect method. Coming to this mass or energy loading, which one we should follow? Mass loading is not the right indicator and energy loading is considered as the right parameter, true indicator of the boiler loading pattern. This all of us should be very clear, because like what I said, mass loading from and at 100 degrees centigrade of the boiler rating is meant only for selection of boiler. With that, its usefulness stops. Whereas in reality, we need to understand what is the energy that is being delivered by the boiler. Here again, slightly different or not found in the textbook. Steam is nothing but a carrier of energy. It's a courier also we can call it. Its job is to capture the energy of the fuel, that is the coal, GCV, and takes the energy to the user point and then dump the energy there and come back to the combustion zone, again pick up energy, go back, give it, come back. So steam as such is nothing but a carrier of energy, and more the energy it carries, higher would be the capacity of the boiler. And we are not per se as such not interested in true sense the quantity of steam, but the quality of steam or the energy content of steam. Energy content of the steam should be high, that's why we go for superheating also. So what is really matter is the energy that is getting transported by the steam. So energy loading is the true indicator of the loading pattern of the boiler, not really the mass. But in reality, of course, I don't mean the academic people, industry people, I mean they really worry about the mass loading, and the mass loading is a parameter which would be different for different industries, and many a times that poor loading of mass can also result in the poor efficiency. And the boiler is loaded to a lesser extent, your loss percentage will become more, the boiler performance would come down. In this sense, we also need to understand this root cause of loading being low, performance is also low. In the sense, steam properties also come into picture. Here you can see that a typical case, we say that mass loading is 52%, 56% for different months, 55, 57, whereas the energy loading is still lower. Still lower. 48.4 is the loading of energy, whereas 52.8 is the mass loading. Of course, here you do not think that the mass loading will be more than the energy loading. It depends on the operating parameters. Now, why do I specify this slide? If the loading is low, you can see that hardly 50% is the loading of the boiler, 50. When the loading is low, naturally the efficiency of operation will also be lower. So people will have to understand this. In the sense, the efficiency comes into play, or its meaning would be clear only when we analyze all these parameters like the fuel quality, fuel size, type of combustion, quantity of air supplied, moisture content of fuel, and also the loading pattern of the boiler. If the boiler is poorly loaded, the efficiency also will be less, because when you do the loss analysis, you will see that the loss becomes 25%. Then you say efficiency 75% is low. Yes, 75% is low, but a partial reason would be loading of the boiler. So the energy loading has to be evaluated by the boiler. Once you do that, then we go for the performance prediction, direct method as well as indirect method. The direct method is known as input-output method, where you need useful heat output and heat input for performance evaluation. Heat output by heat input into 100. Now the other one is indirect efficiency, known as the heat loss method, where we see that BS 845, ASME PTC 41, IS 8753. The sense, when we do the performance study of the boiler, we need to follow any of the standard, and based on which I am supposed to evaluate the boiler performance. And this points to the heat loss method, where we list out various types of energy loss that are taking place, and we establish the numbers through proper instrumentation. In the sense, all the losses are precisely predicted, and then we arrive at the efficiency by summing up all the losses in terms of percentage and subtract it from the 100. So this is known as the heat loss method. Now the question is, which is more reliable? Indirect method is more reliable because it does not leave anything for a chance. Whereas when you go for the direct method, it starts with the MS, steam flow rate. Now there are steam flow meters available online, but again the steam flow meters will have to be calibrated year on year basis, and they are also need to be calibrated with reference to the steam parameters simulated. In the sense, if it's a dryness fraction 98% or 97%, steam pressure is it 64 attar or 52 attar or 108 attar. In the sense, the calibration of the meters will have to be done for the conditions what we will be encountering in the process operation, which is again going to be a tough exercise. So the establishing the steam flow rate precisely on a day-to-day operation is not going to be a easier job, and steam flow meters will have to be a very accurate one, which can be quite expensive. Further, they also need regular calibration, whereas in indirect method we can measure all the parameters very precisely with this simple normal instrumentation, and it will not leave out anything for chance, and this is what most preferred by the industries. And mind you, this performance prediction need not be done on a daily or a weekly or monthly basis. It can happen once in 6 months or once in a year, because these are all the huge capacity boilers with complete automation, especially the power plants. So it is very, very unlikely the parameters deviate during the operation. Again, the important aspect is the coal quality. If it is maintained properly, which happens in most of the cases, the performance of the boiler would not get affected. So even if the performance is carried out once in 6 months, that's more than sufficient to make sure that the operation is on track or not. In addition, in power plants, we have all the parameters available on the dashboard, which also monitors the efficiency regularly. So the performance evaluation of the thermal power plant boilers may be a involved task, but a kind of a task which is quite simpler. It may be time consuming, but it's a simpler one because of the good instrumentation normally you find in thermal power plant boilers. Heat balance, and again this is a methodology we need to adopt while defining the heat balance Sankey diagram. Normally, we should not use the pie charts or any other method of establishing or projecting the performance level. This is the internationally accepted method of projecting the performance. Sankey diagram, we see that the width of the arrow corresponds to the percentage value. Higher the width, higher is the value. So the steam output, it should have a much bigger width so that the percentage is more. Fuel input is 100%. Steam output, that depends on what is the quantity and the quality. This is the Sankey diagram for heat balance diagram. Coming to the losses, normally there are 7, and we classify them into major and minor. Major would be flue gas, dry, underline dry flue gas. Then the heat loss due to moisture. That moisture could come from burning of the hydrogen of the fuel. Like we all know that fuel contains carbon and hydrogen. C goes as CO2, H2 goes as H2O. So that hydrogen getting converted into moisture, that is a loss, because when it getting converted, it absorbs the latent heat. Then you have the heat loss due to moisture and fuel. Fuel would come out with moisture, which we have seen earlier, like coal, 30% moisture, 28% moisture, etc. And air also will have moisture depending on the humidity level. So that also would be a loss. And of course the convection and radiation losses. So these are all the major losses we classify. Major, I mean unavoidable losses. In this sense, these losses, it is unavoidable, and we should also try to make it as minimal as possible. Lot of efforts need to be put in. Whereas the minor losses are concerned, these are all due to the inefficient combustion, I could say, like heat loss due to unburns in ash, heat loss due to CO formation, and other losses. The CO formation is more, indicates that the combustion is not effective. Unburns in the ash, that is carbon content in the ash is more, that again says that your combustion is not right. So these are all the correctable losses. The minor losses, although it is a minor loss, it clearly indicates that we are not doing our job properly in terms of combustion. Whereas the major losses indicate that they are all unavoidable, but they can be minimized. Whereas the minor losses, it's not unavoidable, they have to be avoided, and they have to be not only minimized, maybe we should bring it to as close as possible to nil, because these are all the process inefficiency that results in the minor losses, whereas major losses are inherent to the process which cannot be avoided altogether. So these are all the losses we need to evaluate. And what parameters? Fuel composition. Now you can recollect the quality of coal we are talking about, and we say that there are 17 types. So, and 17 types, there are 17 calorific values, and 17 calorific values will have 17 fuel composition. The 17 fuel composition will require 17 different quantity of air for combustion. So we need to go to the second level of stoichiometric combustion, excess air level, distribution, the sense fuel composition and firing rate we need to establish. Then what is the CO2, that is carbon dioxide, O2, CO1, the flue gas in the operation we have to establish. Then the temperatures of the various streams like feed water, combustion air, flue gas, steam, pressure temperature O2 profile, ash quantity collected at various locations, various points in the sense. It could be at the economizer bottom. In the combustion also you have the zone 1, 2, 3 bottoms. Then you have the air preheater bottom portion. In ESP, electrostatic precipitator, again you will have a zone 1, 2, 3. In the sense, in a power plant, you will be collecting ash certainly from about 8 to 10 locations. 8 to 10 locations, and that has to be collected and analyzed for the carbon in that. In addition, we also need to estimate the quantity of ash collected in each location per shift or per day, and from that we need to find out what is the unburnt loss in the entire circuit. So you can see that these are all the involved one. That's the reason I said this need not be done on a daily basis, but it has to be done on a campaign basis. 3 days at a stretch, all these parameters will have to be collected and then evaluated so that the performance levels are understood during this campaign. All the parameters should be maintained near constant, in the sense you cannot use coal type A on day 1, coal type B, coal type C, D. No, it has to be a same type of coal, because you all know the boiler is a piece of equipment and it would behave according to what we feed. If the feeding is different in terms of quality, it is very likely the performance also would differ. A poor quality coal will result in the higher losses. So boiler is in no way responsible for that. So it's a question of the quality of the fuel, and you also get the quality of the performance of the boiler. So all these parameters will have to be collected, analyzed to establish the performance of the boiler. This is a typical one. Pressure profile across downstream equipments, furnace, bank zone, economizer inlet, economizer outlet, air preheater, electrostatic precipitators, chimney outlet. Because all these parameters, they are all in negative, and it will go to the plus in the chimney, because more the negative one, any air leakage can dilute the flue gas composition, because these are all under negative pressure right up to the ID fan suction. So it is also equally important that the air ingress is not permitted. Again, as I said, the boiler circuit, operating the boiler at the right level is equally important, and equal importance should be given as we give it to the fuel quality. So we need to establish what is the pressure profile also across various what we call as a downstream equipments. Similarly, the oxygen content, you can see the oxygen content 5 to 9.5, which clearly indicates that the air is getting ingress at various locations, and the temperature of the flue gas also comes down 452, 61, 62. These are all the things that indicate that air is going into the system, and we need to arrest that. So these parameters will have to be evaluated regularly, like during the campaign period, maybe once in an hour or once in 2 hours. These parameters will have to be recorded and then noted. Another one, you can see the oxygen percentage and the air flow rate, tons per hour. Oxygen percentage, it varies from as high as 10.79. You can see it is also a function of the steam flow. When the boiler is loaded heavily, the O2 level comes down. In the sense, it is keep on varying. O2 level in the flue gas does not follow any pattern, and it's quite varied. In the sense, these parameters will have to be captured, and then we need to analyze the parameters variation so that we may get some input on that. Yeah. This is a typical performance established for a 120 megawatt AFBC boiler, atmospheric fluid bed combustion boiler. You can see that the efficiency is 86%. Thermal efficiency. And of course, for 500 megawatt boiler and for a pulverized fuel burning, pulverized coal, I mean, it can even go to 89. But reaching 90 is a tough task. And the reason is this: these two, fuel hydrogen and dry flue gas loss. Since we supply excess air, there is going to be a flue gas loss. And since the fuel is going to have inherent moisture, that is inbuilt moisture, because these are the fuel that is mined from the mines, so the moisture would be there, and of course surface moisture also would be there as it picks up. So these two losses cannot be avoided, and they can be minimized. And if these two losses put together in terms of percentage, if it is less than 10, I think we have achieved our goal. The fuel hydrogen cannot be 2%, or dry flue gas loss cannot be 2%. And a solid fuel fired boiler, whereas for gaseous fuel, the performance thermal efficiency can be as high as 94%, I have seen. But on a solid fuel fired boiler, reaching 90 is also going to be a bit of a difficult task. Of course, certainly it should be above 85. Certainly above 85. Here again 120 megawatt, so the low efficiency is slightly lesser. Whereas if we go for 500 megawatt, you can see that this is a 500 megawatt. You can see 89.4 is the efficiency. Moisture loss is 4.5, dry flue gas loss is 4.3. Again, you see that they form the 8.99%. So these two losses are the major losses in a boiler, and effort should be made to bring it low. That's why the flue gas loss can be reduced if the excess air is maintained optimum, and for that only you have seen that oxygen as well as the pressure profile are regularly monitored at various locations to ensure that the dry flue gas loss is minimum. Similarly, moisture loss will be minimum when the fuel has a lower moisture. So you also go for the fuel with the lower moisture content. And this is how a 500 megawatt, when we say, we mean the output of the generator is 500, and we see that boiler loss is 151 megawatt, input is 1428. This is 10%, let's say 10.6% is the boiler losses. So 90%, and you have the condenser loss, turbine generator, work auxiliaries. Ultimately, you get 35% as the boiler overall. In the sense, coal to power. Coal to power is 35%. Of course, my lecture is reduced only to the 10.6, and in coming lecture you will be discussing about the steam, where you lose substantial amount of energy. And this also we do it. Radiation convection losses, it has to be insulation. This is a regular exercise done in a year, once in a year. Thermal images will be captured in the entire steam line to make sure that the losses are as minimal as possible. This is a typical bare surface. And similarly for inadequate insulation also over a period of time, because these boilers, they operate for 350 days minimum. The 15 days is a mandatory inspection period. So 350 days and 24 hours. So they operate certainly for 8,500 hours in a year. And being a abrasive fuel, coal, there is a possibility that insulation gets damaged. So they need to be rectified. So entire boiler will be thermally studied, imaged for all the heat parts, and the losses also would be brought down. What do we conclude? You can see that typically power plant boilers operate at efficiencies exceeding 85%. However, overall efficiency is only 35%. This is the benchmark value. Coal consumption will be, rather I would say, sorry, it's not upward, it should be downward of 0.65. This is called as a heat rate of the power plant. A good value will be less than 2500 kilocalories per unit of power generated. If you really look at that, in India we have more than 100 power plants, 100 power plants. And if the power plant's performance, if it has to be compared, it is done using the parameters heat rate. Excuse me. For that matter, let's take the case of a Tuticorin power plant. You have the Mettur thermal power plant. You have the North Madras, Ennore. How do we compare the performance? Heat rate is the performance, because each one of the plants may be having a different quality of fuel used depending on the cost and the availability. So the thermal performance will not be the right indicator. So the performance of the power plants is indicated by the heat rate. That is what we call as the kilocalories per unit of power, that is energy that is generated, heat rate. And of course, the 85% should be the benchmark, and 90 could be the one what we can achieve maximum. And you can see that for different months, how the Typical coal consumption goes say 0.57, 56, 55. It has gone as high as 0.60. And look at that, the lowest is 0.55, highest is 0.6, but still it could make a lot of difference in terms of cost. And when it is 0.55 or 0.6, again we need to do RCA, root cause analysis, because 0.55 and 0.6 is almost 20, we can say 10% more. 10% could be a tremendous number in terms of cost, so we need to understand why it has gone up. And the benchmark value could be 0.57 total. With reference to export, it is 0.63, because we know that 100% of the power generated cannot be exported, because the power generated would go for internal consumption also. So if you consider the internal consumption as a kind of the energy that is unavoidable, and if you take into account only the power that is exported, you see that it has gone to 0.63. So this is how the benchmarking has to be done. And what are the activities to be done to get the better performance? I think I have 10 more minutes. Control of fineness of the fuel, control of excess air, accuracy of O2. In many power plants, the O2 is the parameter which will be displayed in the control room, and display in the sense it will be displayed like a photograph on a online monitoring, so that every second it will be showing the O2 value. This itself can tell you that how important the O2 value in the flue gas circuit. So this is one of the most important parameters that is monitored on a, I would say rather, every minute the O2 value. Then heat transfer area clean, it has to be kept clean. Air leakage, we have seen the pressure profile, O2 profile, they are all done to keep the air leakage to the minimum. Controlling the flue gas temperature leaving the stack, that is when the economizer or the air preheater, the heat recovery system, when they fail to perform properly due to what do you call that, ash deposits or any other reason, the performance would come down, the stack temperature would go high. So when the stack temperature is more, again we need to carry out the cleaning activities of the heat recovery equipments, optimizing the power consumption of auxiliaries, which you are going to see later, feed water preheating, combustion air preheating, excess air control, minimization of combustion, stack temperature control, etc., will have to be taken care of for improving the performance. Of course, RNC, radiation convection losses, boiler loading again, like what I said, if the boiler is not properly loaded, the percentage loss would go higher. So if it is operating inefficiently or the efficiency is lower, we need to go back and then see what is the loading pattern, and then we need to get from the OEM, equipment supplier, to find out what is the effect of loading on the performance of the boiler. So then that also need to be taken into account, and then the boiler scheduling, too many stoppages again would result in the higher coal consumption, which will also go as a part of the fuel consumption against steam generation. So if the boiler scheduling is not done, in the sense if the efficient loading variation is very high in a day, during a day, performance also would come down. So these are all the areas to be taken care of. And every 1.5% increase in the efficiency can result in almost 10 million tons of CO2 reduction per year. Coal savings could be so much, it could be like 4,500 crores per year. Higher productivity for the same resources, equivalent capacity addition, lower generation. In the sense, I put 1.5%. increase in efficiency, because based on my experience with various power plants of various capacities from as low as 100 megawatt to as high as 500 megawatts single unit. These are called ultra power plant, because normally power plant 210 megawatt into 4 units, 5 units, they would be evaluated for their performance at loads of 75%, 85% and 100%. They will be evaluated their performance for 4500 car, 5200 and 6000 car. In this sense, lot of studies we have done it. It has to be done in a boiler to arrive at the optimum level, and from that experience we found that uh, efficiency increase of 1.5% is really a good achievement for a standard normally well operated boiler. Like what I said, a thermal power plant, it has a boiler efficiency varying between 85% to 90%. Aiming anything beyond 90 is also not that easy, and going below 85 is certainly not acceptable. Like what I said, these two are the two extreme numbers, and maintaining these two extreme, within these two extreme numbers, we also need to understand, like whatever I said, fuel properties, steam properties, air quality, air quantity, measurements of various parameters, regular monitoring. A lot of things will have to be done, and doing all these things, and what you can expect is about 1.5 or 2% increase provided if the boiler is operating at 85% level. If it's already operating at 89 or 90, then we can very well say that the performance is extremely good, and going beyond that can happen only with maybe gaseous fuel or oil fired fuel, which of course we cannot use for the simple reason they are quite expensive. So the concluding remarks are, the performance of the boiler is quite critical, because the cost involved is very high. At the same time, the advantage is the thermal power plant boilers are well designed, well maintained, properly evaluated, and the quality of the fuel also being properly monitored. So in India as of now, but for the age of the plant, the new generation plants are really operating properly well, and any power plant which are within 15 years of installation, they are certain to give very high performance. The ones which are 30 years old, they are slowly being taken off the circuit because of its lifetime. So in reality, performance of the boiler is being done very effectively by all the thermal power plants. They have a good monitoring mechanism, dashboards, and they also go for the external evaluation of the performance of the boiler on a yearly basis, and they maintain the efficiency level well. The only scope now available for fuel cost reduction is going in for alternate fuel using the biomass also, but again the availability is a question mark. So the power plants now, they adapt what you call the alternate fuel to bring down the cost as well as the CO2 emission. As such, the overall scenario in India as far as power plants are concerned is, the performance levels are certainly improved now, and their efficiency levels are high. I think with this I will Acha. And these are all the emergency condition, because I thought I should also inform this. Normally we also do it to the power plant to ensure that these are all the parameters maintained from non-stoppage. As I said, the performance can deteriorate once if the parameter that have to be maintained are not maintained. Water level, furnace dot, bed temperature, excess boiler pressure, furnace explosion dose, boiler feed water pump failure, all these things will have to be properly monitored for the performance, so that the plant does not stop. Once the plant is not stopped, then automatically performance gets improved. Thank you very much for the listening. I think it's 1:28. So if there are any questions, maybe the organizers can initiate. Thank you.
Yes, sir. Participants, if you have any questions, you can raise now.
Yes. It was indeed a very nice presentation. Actually, I wanted to know whether it is mandatory to have energy audit every year for such utility boilers.
It is not mandatory. It is not at all mandatory. One thing is okay. In energy audit is mandatory for the process industries in some states, not in all states. That is the first point. The second thing is the thermal power plants, they come under what you call as the designated consumers. There
Yes.
are about 15 plants, 15, what should I say, that industries classified by Bureau of Energy Efficiency as designated consumers. And thermal power plant is one. So for them, they have to do it once in a patch cycle. They call it cycle 1, 2, 3. That goes every 5 years. And they have to have the benchmark. They have to maintain a lot of parameters are involved in that. So the power plants come under that category, not in the mandatory category. In fact, that is much more than mandatory. The
Sir,
patch
and one more
cycle.
question. Yeah,
Sure.
when these boilers get certificate renewed for continuous operation, there also, is there any check on energy usage or this benchmarking?
No. The
No.
boilers are certified for their operation, not for the performance. Like they go for the bed coil, let's say, or the coil thickness and then the fan rating, etc., etc. They don't check for the performance, because one thing what we need to understand is the performance of the boiler is the operation oriented. It is like driving a car. A good car can be made to operate inefficiently depending on the driver. So a boiler certification is done for the parts, not for the operation, and it doesn't certify the performance.
Okay, thank you.
Thank you.
Participants, any other doubts? Okay, sir.
Thank you.
Hello.
Thank you.
Yeah.
Sir, is there any exam to act as an energy auditor?
Is there any?
Is there any examination to act as an energy auditor, or anyone can do it?
I don't understand. Anyone can do what? Performance
So
study
he is
or?
asking about
Sir,
energy
my
auditor
question
exam.
is there any exam or procedure to act as an energy auditor, or
Yeah,
any
there is.
person can do it?
Mr. Dr. Venkat,
Tell me, sir, please.
you can answer this.
Yes, sir, of course. Sir,
Yeah.
there is one agency informed as BEE, Bureau of Energy Efficiency. They have these annual examinations, wherein two examinations would be available. One is for energy manager, another one is for energy auditor. 4 papers, it will be available there. If you can clear 4 papers, you will be a certified energy auditor. But for auditor, some experience in an industry is mandate, sir. If you don't have the experience, you can appear for energy manager examination, sir. And for additional information, refer the site, sir, energymanagertraining.com.
Okay, sir. Okay, thank you.
Okay, sir. You have cleared all the doubts, and thank you very much for spending your valuable time with us, sir. And your session was very informative to all the participants, sir.
Thank you.
Thank you very
Thank
much.
you. Thank you very much. Thank
Thank you,
you.
Professor.
Thank you. Thank you. Bye.
Thank you, sir.
Participants, now it is time for lunch break. The next session will resume at 2:30 p.m. You can join the next session by 2:30 p.m. Thank you. And please submit your feedback come attendance form.
Shyam, have you informed that feedback for every sessions like?
Yes, sir. First session already we received the feedback, sir. I'm sharing the
Yeah.
link in WhatsApp group.
Yes, sir. In fact, attendance also has been downloaded in Teams. So, in fact, the feedback form would be an additional option.
Yes, sir.
Sir, hello, sir.
Hi.
Tell me, sir, please. Yeah.
Yes, sir. My WhatsApp number is not working because of some problem has come. So I've not given the feedback, sir. I've joined from the day, from the first session also. So wait, can you please, can you help me out?
Shyam, there is one option, but you can also email them actually after the end of every session or halfway through the session. You can email it to them, like whoever are able to access their emails, they can have those things done through their email or through their WhatsApp also.
So feedback have given to mails also, you are saying?
Yeah.
Okay, sir. Thank you.
Yes, sir. Sure, sir. I will share the feedback link to their mails also. Sir.
Yes,
Yes,
Thank
sir.
you.
Okay, fine. But thank you, but thank you all.
Thank you, sir.
Sir, if this chat provision is out, then it would be better, sir.
Chat provision, Shyam, please work on that aspect, whereby if it is enabled, it becomes helpful for all, whereby they can raise their things also.
Yes, sir. But most of the participants are entering as a guest, so they don't have access in the chat box, sir. You will check it.
Only
Yes, sir.
registered MS Teams only can enroll or what?
Yes, sir. They are only getting the access of chat box. So remaining all are as a guest. They are not getting access for the chat box, sir.
Okay.
Okay, but anyway, you have a check, sir, and probably if there is anything that has to be addressed, you can WhatsApp us, sir.
Okay, sir.
Sir, feedback form not yet received, sir. Can I expect?
Sir, 5 to 10 minutes, I will share the feedback form through mail also, sir.
Please.
We already shared the session 1 and session 2 feedback form in the WhatsApp group.
Sir, session 1 also you can send to me, sir, please.
Sure, sir. Sure, sir. I will
Sir,
mail
okay, sir.
Thank you, sir.
Thank you all. If there is any additional queries by the participants on FDP, it is welcome. Thank you all.